this, we would like to thank and acknowledge our sponsors, Boyce Astro and Chroma Technology. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation, surgical devices, machine vision, multispectral imaging, and of course, our favorite, astronomy. Please do check out their website to learn more about what they do. You can see that on the screen. Okay. Now, ladies and gentlemen, your instructor for today is a professor emeritus in astronomy and astrophysics and science education at the University of Toronto. He has been actively involved with the AAVSO for over 40 years and served on the council for 11 years, including 3 years spent as president. More recently, he spent a decade serving as the editor of the Journal of the AAVSO. Fortunately for us, he is not only an expert on the science of variable stars, but also on being a stellar teacher. You might already be familiar with his teaching through the AAVSO's hands-on astrophysics curriculum, which he co-created with Janet Maddy. His skill in education and outreach has earned him quite a few awards, including the American Astronomical Society's Education Prize, as well as the 6th AAVSO William Tyler Olcott Distinguished Service Award. It's small wonder when you consider that through his mentoring, he has helped high school students to publish over 60 papers in the Journal of the AAVSO. Today, he is here to share with us some of the projects that he's done with his students and how you can continue the research yourself using AAVSO's data and tools. Today's how-to session is already shaping up to be a great one. So let's jump right in. Ladies and gentlemen, without further ado, please allow me to introduce to you one of the best variable star teachers in the world, Dr. John Percy. Welcome, Dr. Percy.
Okay, let's see if we can get our screen working here. Lauren, are we okay?
I don't see it yet.
Oh.
The share screen button should be in the bottom center of your screen on the Zoom window.
Now how are we? Can you see?
Right now it's in the edit mode. So if you close your screen share, the Zoom screen share,
Okay.
and then start it again, and this time choose the option, I believe it's the first option, and it allows you to share your whole screen, not just a single window.
Any better?
Much better. Looks great.
Okay, are we set to go?
Yep.
Okay, Lauren, if there's any technical problems, just let me know and we can start again. Sorry about those we've had already. Okay, so I'm just amazed that there's so many people here from so many different places around the world. And so let me begin. Now, it's traditional up here in Toronto that if you have a Zoom meeting of any kind, then, whoops, we are having a problem already. There we are. Somebody has to show a cat. So I've shown a cat. My cat is asleep right now, and that's the best that I can do. Okay, but more to the point, let me introduce my students. And they are mostly undergraduate research assistants, some in the winter time, some in the summer. My winter students have just finished their work now. You'll probably see it in JAAVSO in a few months, and just started with a summer student. But for about 25 years, we also were able to include outstanding senior high school students in our research program. And again, many of them published articles in JAAVSO and other places. And this just happens to be 3 of them here. And if you have some opportunity to introduce young people to variable stars, this is one way you can do it. It benefits you, it benefits them, and so on and so forth. So always my goal in this work with students is so that they can develop and integrate their skills in science, math, and computing, and motivated by the excitement of doing real publishable science with real data. Very often that's AAVSO data. More recently, we've been using data from the ASAS-SN database that I'll tell you about a little bit about later on. So these are my biases here. I happen to be working these days on pulsating red giants and supergiants, and also yellow supergiants like RV Tauri stars, and particularly most recently the semi-regular yellow supergiants related stars. But in the past, I've worked on a variety of other kinds of variable stars, even including things like young stellar objects and RS-Can-Venn stars. And then initially I was involved in actually modeling stellar structure, evolution, and pulsation. That was back in the old days. So how can you take part in the same things that I do with my students? Well, one thing you could do is to mentor students yourself. I suspect that a few of you out there are professional astronomers and educators who are in a position that they can do that. But it's something you can do. I mean, I know that many of you observe, but here's something else that you can do astronomically speaking. And I assure you that you get great satisfaction of analyzing and solving some particular star. And particularly if you have a chance to disseminate, which I hope you will, either at AAVSO meetings or at your local club, or something that you can contribute to BSX, or if it's a substantial project, then you can even think about sending it to JAAVSO. We do publish papers by a wide variety of people, both amateurs, professional students, and so on and so forth. And one of the things that us section head leaders are there to do is to help you in doing this kind of thing. So the question is, observe or analyze? I know many of you observe, and many years ago, my students did observations photoelectrically from our campus observatory. The problem is that Toronto is a climatically underprivileged city, and there were also problems of students working at night and so on and so forth. So we turned our attention to analyzing. And particularly since there's good data there that's never been analyzed before. And by publishing the results of this, the observers, AAVSO observers, see what kind of science has come from their observations. And of course, the students learn how to do analysis and how to do science. But it would be great if your students could at least contribute one observation to the database before they actually use all the other observations that are there. In terms of getting started, I can modestly suggest that you track down my book. It's available in electronic versions as well as being sold on Amazon and places like that. There's a huge amount of information on the AAVSO website, and there's many articles in JAAVSO, review articles and research papers, which are a very good way for you or your students to get started. What about data? Well, obviously, there's the AAVSO database, which is an incredible database that goes back over 100 years. More recently, there's photometric data from photoelectric photometry, CCD photometry, and so forth. Recently, I've been using for my students the data from the All-Sky Automated Survey for Supernovae, or ASAS-SN as we call it. And I'll be showing you a few examples of that kind of data. And for analysis, either VSTAR, which is the AAVSO's wonderful time series package. There are other time series packages available, and occasionally you'll get students who actually want to code their own particular approach to time series analysis. So what kind of things can you do, or what can students do? One rather mundane thing is to actually figure out whether variable stars are variable or whether they're not. And some years ago, Emil Terzieff and I started looking at the many suspected variables in the AAVSO program. This is one example here. This is ISGEM, and the data are absolutely constant within the errors. We told the AAVSO that, but they continue to observe it for whatever reason they do. One of the things that can benefit from this is being able to tell observers which stars are variable and worth observing, and which ones could actually be removed from the program. Then there's unusual stars, and you may know about this communication that comes out every month, and it had great long lists of stars of interest. Now the question is, are those ones that you could analyze? The problem is that stars of interest get into the communications usually because some professional astronomer wants to analyze the data of them anyway. So you have to be a little bit careful in choosing those for analysis. I'll show you a couple of mine that are on the stars of interest list. One is B725 Sagittarii, which changed from a Cepheid with a period of a few days into a pulsating red giant with a period of almost 100 days. And that's really quite unique behavior. In fact, one thing that you analysts out there can do is, from the massive surveys of stars that are done, find the ones that are doing something that's really unusual. And I'll give you an example or two later on, and use these to analyze, because it's quite likely that nobody else is going to analyze them. Here's another example. This is RU-CAM, the Cepheid that stopped pulsating. This is its amplitude, or rather the semi-amplitude. This is from the AAVSO database here. And so back before the 60s, it had full amplitude of about a magnitude, and then it suddenly decided it didn't want to pulsate anymore. And so the amplitude has come down to essentially 0. It may look at towards the end here as if it started to pulsate again, but that's really because there's so few observations here that just errors in the observations can make it look as if the star is actually variable. So this is another example of an interesting star that deserves to be looked at. Now, one of the things that I've become particularly aware of recently is the importance of looking carefully at the light curve before you do a lot of fancy analysis. And I'll show you a few examples here. This is some work dating back over 100 years by a largely forgotten Norwegian amateur by the name of Sigurd Enebo. And these are his observations here of RV Tauri. And you'll notice quite clearly here that it's varying with a period of about 40 days. And furthermore, alternating minima are deep and shallow. So alternating deep and shallow minima. And then again, it's got this slow variation here. So three interesting things. It's pulsating in an unusual way. It's got these long-term variations, and that just jumps out at you from looking at the light curve. So be quite prepared to look at light curves before you start doing a lot of fancy computer analysis. Here's another magnificent example. This is UMON, which is an RV Tauri star. And back in the 1990s, when AAVSO data was first available electronically, you could plot out in a minute or two the entire database going back for a century. This is something that immediately struck my attention because this star, as well as having a 92-day pulsation period, which you can't really see here because of the compressed time slot, but you can see these minima that occur about every 2,500 days. And you can notice that they're not all the same. They almost disappear more recently here. So the eclipse cannot be by some solid star. It's got to be by something dusty, which can vary its eclipses from one eclipse to the next. And so this introduces us to this very interesting behavior of many RV Tauri stars. And they're subclassified as RV subtype B to show that they have these long secondary periods due to the eclipses. Here's another star that you've probably heard of recently. This is Betelgeuse. And you may have heard a couple of years ago that it went in an unusually deep fading. This is a light curve of the AAVSO photoelectric observations, and indeed it went down almost to plus 1.5. But you also notice from this light curve here that it's gone relatively deep other times before. And indeed, if you plot out the whole visual light curve for this star, you'll notice that there were deep fadings 2 or 3 times in history, going back 100 years or so. And so the recent fading is not a one-off, unique kind of phenomenon that has never happened before. In fact, if you analyze the AAVSO observations, which I and my students have done, you find that Betelgeuse has a pulsation period of about 300 days. And it also has a long secondary period, about 2,000 days, like the RV Tauri stars that I just showed you did. And both of these have variable amplitude. We have no idea why these pulsating stars vary in amplitude from one cycle to the next. But in any case, what happened 2 years ago was that the stars' 300-day and 2,000-day periods were both at minimum, and their amplitude was both at maximum, so it produced the deepest possible combination of those 2 different periods. So again, you can start to understand that simply by looking carefully at the light curve, whether the photoelectric or the visual one. Here's a more recent example. And I mentioned the ASAS-SN catalog, which has about 500,000 variable stars in it and data which any of you can download for free. It's completely open. And what ASAS does is that it automatically analyzes the data from each of the variable stars in the database. It does this by computer, just a dumb computer with no human involvement of it. And it determines a period. So for this particular star, which is a red giant, it said that the period is 417.9727 days, which is an unreasonable degree of accuracy, considering that the database is only about 5 years long. But what it's done here, in one phase here, it's got 3 cycles, not 1 cycle, but 3 cycles. Here's the light curve here. The period is actually 1/3 of 417.9 days. And so just by looking at the phase curve and the light curve here, you can tell that the computer really got the wrong answer. The answer is 1/3 of 417, not 417 itself. And it matters if some other astronomer is using that database and thinks that this is a red giant with a period of 417 days. By the way, the problem here is that this star, like most red giants, doesn't behave exactly the same from cycle to cycle. It's like Myra itself, if you've ever observed that or looked at its light curve. So that's another example of just simply looking at the light curve. Well, having looked at the light curve, you can then actually go on and do some time series analysis using VSTAR or a package like that. And the graphs that I'm going to show here are from VSTAR. I like to work in frequency space. Frequency is just 1/period here. So this particular star, RS10, has 3 periods. There's 1, there's 2, and there's the third one there. The periods are 90 days, 160 days, and 966 days. This is a red giant. The first two periods are two different overtones, and the third, which I'll say more about in a few minutes, is the mysterious long secondary period of this star here. Now, one of the reasons that I like to work in frequency space is that we encounter something called aliases. Aliases are actually, what should we call them? They're not a real period. They're a spurious period that you get, and they're always separated from the real period by 0.00274 in frequency, and that's 1/365.25. In other words, they're separated by 1 over a year. And the reason for them is that the data inevitably have seasonal gaps every year. And the result of doing Fourier analysis with data that has those regular gaps is that you get aliases. Now, it's important to know which are the aliases. They jump out in frequency space because you can also get real signals. This period, this peak here, is a real period. It's an overtone period. Most likely this star is pulsating in the fundamental mode and in the first overtone mode. And that's really important because now you've got two pieces of information about that star that you can compare with theory. Not just the one period, but now you have a second, and in some stars you actually have a third period, and so forth. So you have to be very careful with time series analysis. It's a kind of an art that you need to get a bit experienced with. Now, if you do time series analysis on stars that aren't completely regular, then things get complicated. And this is from my latest article in JAAVSO. It's posted on the JAAVSO site. And the title of this is, what are the semi-regular SRD stars? SRD stars are semi-regular yellow supergiants. And so the question is, well, why are they semi-regular? Well, it certainly jumps out in this light curve here because, first of all, there's a slow variation going on here in addition to the pulsational variation. And the pulsational variation has a variable amplitude. So you've got two different things here that are causing the star to be not regular. That is, you can't just phase all the points together and get a perfectly smooth phase curve. So stars are a bit more complicated sometimes than you might actually think. Well, another thing you can do with VSTAR, it has a package in it for wavelet analysis. And wavelet analysis is basically a technique where you can take a Fourier analysis and simply take it right across the database from the beginning to the end, and at each point determine the best period and amplitude at that particular point. So this is an example of a project that my student Sarah Haroon did a year and a half ago using AAVSO data. So it extends for about a century. This is for AV Cygni, which is one of these yellow supergiant pulsators. And you'll notice that if you take the period from the wavelet analysis plotted against Julian date, it's actually slightly sloped. That is, there's evidence that the period is slowly decreasing. Now, that's actually marginal with this data here. The data is really not as dense as we would like it to be, but the method works. And so it's a different thing that you can use wavelet analysis for. And you can also use it to study the changing amplitude of the star. Okay, this brings us to the Percy list. I'm the co-advisor to the LPV section, long period variables. And one of the things that we do is to suggest to observers, well, which of the long period variables in the AAVSO program, and there's thousands of them, which ones are doing unusual things. And so I've got a list of 50 or 70 stars there that are particularly interesting, and this is one of them, RU Vol. And you can immediately see here that the amplitude, as measured by the scatter and the light curve, has gradually decreased. The larger points, as you perhaps know, are Johnson V photometry, photoelectric photometry here. So now you can use VSTAR. You can use the wavelet routine here to measure the semi-amplitude versus time here. And again, this is almost a century of data. And you can clearly see that the amplitude of the star has slowly decreased. In fact, it's almost down to zero, though not quite. And likewise, you can look at the period, and the period starts out at about 155 here, and by the end of the data set, it's down to something like 80 or 90. Now, you sometimes get regions here where the diagram gets scattered. That again is usually because the data is very sparse in this region, and simply the errors on the visual observations are enough to give you a spurious answer. But you can certainly see that the period is changing quite substantially. And that means that the star is undergoing some very rapid change in its size, because the period of vibration of a star is roughly proportional to the radius to some power 1.5 or 2 or something like that. So what you're really seeing here is the changing radius of the star. And you can also plot this out on the contour diagram here, where you have the period vertically, the time horizontally, and then the equivalent of the power or the amplitude is the color plot here. And so you can see that, first of all, the amplitude was large at the beginning, and you sort of see that it's getting smaller, but you can also see that the period is gradually declining here to something of the order of 80 days. So this is the sort of thing that you can do with VSTAR on the different stars in the Percy list. Some of them have variable periods, some have variable amplitude, some have slow variations that they're undergoing, but they're all interesting. And if you go to the website for it there, it tells you what it is that is interesting about it. Now, I want to say a little bit here about long secondary periods in long period variables, because first of all, this has been a mystery for about 100 years. And secondly, the AAVSO observers have played a substantial role, really, in understanding this. And my students have done a lot of the analysis here. This comes from a project by Emily Diebert. This was her first research project when she was an undergraduate. She's now the superstar PhD student in our graduate program. So she's gone on from here to really great things. So this is a star Y-Ling, and what we have here, this is a star that has a pulsation period of 134.7 days. That's not shown here because this is a much longer database, but what we've done is we've averaged the observations in bins of 135 days to suppress the pulsation. And now what we find are these long-term variations here that occur on a time scale of 1,260 days. And usually the LSP is about 10 times or slightly less than the pulsation period. So the question is, what is it that causes these long secondary periods? And there's been a number of, whoops, we've missed something here. Let me see if I can get back to the previous slide here. Somehow a slide has gotten missed here. But the solution to this came last year in a paper by Iwan Szynski and his Polish colleagues. And what they discovered here with very strong evidence was that these are red giants which are being orbited by a companion star that was initially a planet, but it accreted matter from the stellar wind of the red giant and has grown to a mass of a brown dwarf or a very low mass star. And first of all, that causes binary motion in the long period variable, which has been observed. And also it causes these eclipses here. The way that the problem was actually solved, this is an artist's conception here from a review paper by Iwan Szynski. The companion is embedded in this dust here. And so the long secondary period is when the star itself gets eclipsed. Half a cycle later, the companion with its dust is behind the red giant. And if you observe this in the infrared, you observe a secondary eclipse, which is the eclipse of the companion star, which is primarily emitting infrared radiation because of the dust around it. So it was a beautiful piece of work in which the AAVSO played an important role. One of the more recent things that we've been doing is looking at long period variables in globular clusters. So you may know that globular clusters are among the oldest objects in our galaxy, roughly 10 billion years old, and very deficient in elements heavier than hydrogen and helium. And so what we find, and other people have found this in a less distinct way, is that first of all, these stars here undergo a slow variation. This is the long secondary period here, which in this case is the order of 300 days. But you'll also notice if you look carefully here that the brightness is going up and down on a time scale of something like 40 days. The 40 days is the pulsation period, and then it's the long secondary period as well. And indeed, Pratik, who was the student who did this last summer, has found that almost all of these red giants in globular clusters have long secondary periods. And if you believe the Szysinski et al. Mechanism, then that must mean that these stars started out having planets which could then accrete matter to become more massive, like brown dwarfs or low mass stars, to cause the radial velocity variations that we see in the red giants. Another thing that we find in virtually all these stars is that the amplitude of the pulsation, and you can see it in some of these cases here, is highly variable. It varies on a time scale of about 18 pulsation cycles. And nobody has been able to figure out why these stars, the red giants, or for that matter, the yellow supergiants, the RV Tauri stars and the SRD stars, have these variable amplitudes. As far as I know, the first observation and study of those came from the analysis of AAVSO observations as done by my students. So I'd like to just finish up with a few projects that I and my students are working on right now, because we've pretty much finished our half hour here. One is going back to the original discovery papers of the long secondary periods, and that should be LSPs, not LPVs, sorry. These are the long secondary periods, and they go back, as you see here, to 1933. And by the time you include Payne Gaposchkin's stars and Nancy Hauk's stars, and she, in fact, compiled a great long table of these. And so these were all supposed to have long secondary periods. So what I am doing right now is going through the AAVSO visual observations of these stars to see which ones indeed do have long secondary periods and which ones have turned out not to. And that's going to provide a century of observations and analysis of this still quite mysterious phenomenon. Another thing that I'm working on, and my students going to be doing some more work on the SRD stars this summer, and this is the paper that on the AAVSO VSTAR, the JAAVSO website right now, is on the question is, what are the SRD stars? Why are they semi-regular? So this is what why I found. I looked with the ASAS-SN data at 37 of these stars here. 30 of them show significant amplitude variations. We don't know the cause. 11 had periods that kind of wander by a few percent, something that long period variables, Mira stars, do very noticeably. Some of them abruptly shifted in their period, not sure why. 7 showed a possible long secondary period. Presumably, these are like the RV Tauri stars, like RV Tauri itself, that have the slow variations and are also due to a companion enveloped in dust. 8 of them showed possible double mode pulsation. That is, you get 2 periods instead of 2 periods for the price of 1, or varied in some other complex way. So not surprisingly, these are all classified as semi-regular stars. So one of the things that shows us is that for many variable stars, the simple period and amplitude that you find in a catalog like VSX or the general catalog of variable stars is completely insufficient to describe the behavior of these stars. The period may in fact wander. There may be more than one period. The amplitude may change, et cetera, et cetera. So there's a lot more to variable stars than just a period and an amplitude. Another paper that I might steer you towards, I do a regular column in the Journal of the Royal Astronomical Society of Canada. This is an open access journal. You can track it down. And so earlier this year, I tried to put together a few of the things that I and my students had done here on different kinds of stars. The RV Tauri stars like UMON and RV Tauri that I showed you, the SRD stars, many of which have long secondary periods, the long period variables like Ylin that I showed you, possibly even Betelgeuse. And it may be Betelgeuse has a long secondary period. That may in fact be because it has a companion. It does vary in radial velocity with a similar period to its long secondary photometric period. So who knows? And so this phenomenon of having a dust-shrouded companion orbiting the variable star regularly is something that this is a hypothesis, but it's something that really comes from studying AAVSO data over many decades and seeing the connections between these different kinds of pulsating stars that are on the AAVSO program. Okay, I'd like to stop at this point for questions. We have most of half an hour, I think, for your questions or discussion. I just want to thank the observers who made the measurements, the staff who archive them and maintain them. It's not easy. The group that developed VSTAR for International Year of Astronomy, my 100 or 150 students over the years, my colleagues in the AAVSO, and a few of you are actually out there today, my university, which has been very supportive of the work that I do with AAVSO and its members and observers. Also to Lauren and the other organizers and sponsors of this webinar, and thank you for attending this. So that's the end of my presentation here. Lauren, are you still there?
Yep, right here. Thank you so much. That was an yeah, no, not flooded out here, not yet.
Okay.
All right. Thank you so much. That was an excellent presentation. We do have several questions already lined up, so let's jump right in. So first question was, can high school students contribute to this kind of work? I feel like you partially answered that through your presentation, but maybe you'd like to talk some more about how you involve high school students in this.
Okay, the ones that I had for something like 25 years, and 3 of them were on the first slide that I showed you there, but there were almost 100 of them in total over 25 years. They worked within an official program of the University of Toronto called the Mentorship Program. And the idea was that they could work with me in the same way that an undergraduate student could work with me. And I found they were more than competent enough to do the kind of analysis and computer work and understanding that a second or third year university student could do. So it was a reasonably structured program. And I think that a talented high school student could certainly do this work. It would probably be difficult if they didn't have any kind of mentoring or instruction at all. So it's the kind of thing that I think would work best if they had some mentoring or a connection with a club or some program that the AAVSO was running in a formal way. Any of you out there who are instructors at the high school or college level, you could certainly get your students involved in this kind of thing. Incidentally, if you simply search for my papers, either the journal ones, you can search the Journal of the AAVSO and get any papers of which I am an author, or there's a service called ADS, the Astrophysics Data Service, which you may have access to, and you can also track down papers by me or papers that have certain words in the title or abstract or whatever.
Mm-hmm. Okay, thank you. And quite related, we did have a question come in on Facebook that was asking if you had some specific suggestions for instructors to begin with getting high school students involved in this. Like, are there any existing programs that you know of right now that other instructors out there could look into or something like that?
Well, one thing that's buried on the AAVSO website is what we originally called hands-on astrophysics. It's now called variable stars. And so if you go on the education page, then somewhere towards the bottom, you'll find VSA or variable star astronomy. So that was basically a whole curriculum that Janet Maddie and I created for International Year of Astronomy. Or well, actually, it was earlier than that, but it sort of mostly got finished by 2009. And there's a huge amount of information there that's specifically designed for a school kind of setting. Otherwise, I'm not particularly sure. There was a review paper that I gave 2 or 3 years ago about my 40 years of supervising students. And it's that annual series of conferences on robotic telescopes and student research. And I can't remember the exact title, but you can probably Google it. And so it's a slightly more structured explanation of what I've been doing with my students. And I've tried in this presentation here to suggest a few areas that might be worth following up in small or larger research projects.
Thank you.
And I've only talked about long period variables and yellow supergiants. There's also lots of interesting projects in young stellar objects. And a lot of this can be done using the ASAS-SN database. There's another database which I know about and I'm really tempted to get my students involved in. It's called DASH, D-A-S-C-H. And it's basically the digitized data from the Harvard plate stacks, the 500,000 photographic plates. And so I have looked at that and there's data there which I guess has hardly been analyzed at all. And particularly for stars like long period variables, I think there's a heck of a lot that could be done. Another thing that I haven't really done much of and that could be done is actually merging different databases, merging the AAVSO database with others like ASAS-SN. DASH is a bit different because it's mostly photographic magnitudes and so forth. So there's huge amounts that can be done. There's huge amounts of data that have never been analyzed properly until now.
So much potential. It's exciting. Okay, so actually what you've just talked about is quite closely related to 2 more of the questions that we had in the queue. Well, actually one's a comment. Let's go with that one first. This is from Michael Poxon, who recently gave a fantastic how-to hour on young stellar objects. And he says that the young stellar object group is currently looking closely at V347 Aurigae, which is a weird EX Orionis possibly type star. And he submitted that as a comment early during your presentation. So I'm not sure what slide exactly that was.
Okay. Now, it's interesting, but let me tell a little story here, because this involves one of my high school research students from some years ago. And the story goes way back, something like 30 or 40 years, when Janet Maddie was the director. It was fairly early in her time. But you know that the AAVSO gives awards for observers who make a huge number of observations each year.
Mhm.
Well, there was a very famous amateur astronomer by the name of David Levy. Everybody knows about David Levy.
Mhm.
And he discovered that one of the ways that you could really run up your total for the year was to study nebular variables, that is, the young stellar objects in the Orion Nebula and so forth. And so he ran up thousands and thousands of observations. And finally, Janet got fed up and said that from now on, I'm going to discount observations of these stars by a factor of 10. Well, by that time, another graduate student in our department, Bernard Bois from Quebec, was doing the same kind of thing. Well, anyway, something like 20 years ago, when Janet was still alive, bless her, I said, well, what had happened to all of these observations that David Levy and Bernard Bois had made? I think actually, excuse me, I think Elizabeth Wagon was very much involved in this and ended up doing the actual work. And the answer to my question was, well, they'd never been validated. So I said, well, could you actually validate these visual observations of young stellar objects? And they said, okay, well, we'll do a small number of them. And so they sent me these observations, and my high school students started to look at these. And you may know that one of the standard things that young stellar objects do is they have rotational variability. So they're spotted, but more so than the sun is. And so as they rotate, they vary with whatever the rotation period is. And the rotation period is extremely constant. And it means that if you do Fourier analysis of lots of observations that are visual and therefore not very accurate, you can still pick out a very weak signal. And in fact, they were able to pick out variability of 0.03 of a magnitude in this database of visual observations. It's a case of how Fourier analysis can be used to beat down the error which is inherent in visual observations. So that's one of my more interesting stories. So yes, there's lots in young stellar objects that could be done. Just consult Michael or someone else. The long-term advisor to that section was Bill Herbst, who's a great friend of mine. We're a graduate student, or he was a graduate student in my department many years ago.
Mhm. Wow, that's fantastic. I never heard that story for sure, but very interesting. Okay. Oh yes, and the other thing, you mentioned the digitized Harvard plates. So Leo Fernig had a question. He asked, do you know anyone who is working with the data from the Harvard notebooks? So not the plates, but the notebooks. He says that he's been transcribing for the Zooniverse Star Notes project for 18 months, and he's seen many pages of magnitude estimates dating back to the 1890s.
Well, I did see something recently which used the dash data, but I can't remember. So the best thing is to go into either the JAAVSO search or the ADS search and search for things that say DASCH or Harvard plate magnitudes or something like that, because I honestly can't remember where I saw it. But I've seen hardly any references to the use of that data. But I did look at it a few days ago, and I kept finding interesting stars there. Not every variable star is in a field that's been analyzed so far, or it's been digitized. So not every star is there, but I found lots of my favorite ones, and there were observations there that could be used. The accuracy is not terribly great. It's not even quite as good as visual measurements on average, but again, there are lots and lots of measurements of some of these stars. So it would be worth looking into as a project. And if it was published in JAAVSO, then other readers would get an idea as to what kind of things might be done on using that database. It's something that can be used to expand our database on some of the long period stars that are also on our visual program. As I said earlier, the Harvard stuff is photographic magnitudes primarily, and so you can't directly convert it to visual magnitudes.
Mm-hmm. Yeah, that's a great idea. Okay, thank you. So we had several questions come in that are related to the practical side of doing projects. So first of all, here's one from Moses Montero who asks, where can we find comprehensive guidelines about how to perform data mining?
Well, you could read some of my papers. I mean, it explains what we have done to mine certain kinds of data. I always recommend the manual that goes with VSTAR. It certainly deals with some of the practical stuff, though not all of it. One piece of advice, for instance, that I would recommend is that when you use the Fourier part of VSTAR, you do have the option of running what's called a standard scan, and it looks at the largest and smallest periods that could possibly be identified in the data set. And I always recommend doing that because you never know when there's going to be a signal at some period that's much longer or much shorter than what you're expecting. Mm-hmm. And so when you start some of these analyses, you shouldn't always assume that you know the answer before you do the analysis. Other than that, maybe somebody else might have a solution and might want to either put it in the chat or post it on one of the forums.
Mm-hmm. Yeah, okay, great advice, thank you. Okay, next question. This one comes from Jim Williams, who asks, okay, in the broad sense, how would someone go about getting started with this? Specifically, how do you find, start, and execute a project? So I think I recognize the question that Jim's asking here. It's about defining your research question. How do you do that?
Well, I guess first of all, you have to be curious and simply spend a little bit of time looking at random light curves of things in the AAVSO database. Now, many of you out there, you have a particular kind of variable star that you have been observing. Some of you might be young stellar object types. Some of you might observe long period variables or cataclysmics or our Corona Borealis stars or something like that. And so that might draw you to analyzing that particular kind of star. When I looked at the DASH database, one of the stars that I looked at was our Corbohr, and yes, it was doing all the things that our Corbohr stars were supposed to do. Mm-hmm. Okay. But again, there's section leaders for each of the observing sections, and I think that they can advise not just on the observing, but on the kind of analysis that you could do. I mean, one of the things that I really recommend is that you start giving presentations to your local astronomy club. I bet most of you belong to at least one local astronomy club. I belong to the RESC Toronto Centre, and I occasionally will give short presentations on variable stars in the hopes that people will get interested in them. Or you can publish your little article in the newsletter of your local astronomy club if you want, or you can simply start your own website and do your own blog on whatever it is that you want. But it's the sort of thing where you've got to dip your toe in, get your toe wet, and look around and get a sense of what's there. look at things like the Percy list or other such things.
Mhm.
Look at some of my papers.
Great advice. Thank you. Okay, next question here. This one asks, is the VSTAR data accepted by peer-reviewed publications? And what is the standard format for citing VSTAR?
The first the first answer is yes, it certainly is accepted. VSTAR is a perfectly good time series package. It's used by many, many different people. My papers are accepted by the AAVSO journal, which is fully refereed. Others of my papers are in things like the publications of the Astronomical Society of the Pacific. There is a standard way of referencing that. If you just look at one of my papers, it's basically an acknowledgement to Ben, who was the main developer of it, and there is a link to one of his articles. The reference has actually changed. So if you look at my SRD article, which is up on the JAAVSO site right now, just look at how that's been acknowledged. But no, it's a perfectly good package. I recommend it.
Great, thank you. Okay, next question. Here's one I like a lot. It's coming from Bob Buckheim, who asks, an increasing number of AAVSO observers are capable of low resolution spectroscopy in the realm of R500 to 1500, let's say. My suspicion is that consistent spectro and photometric monitoring of some of these stars in combination over several years would be quite useful. If that's true, could you offer some suggestions of specific targets that would benefit from this combined monitoring with spectra and photometry?
Well, first of all, I could probably refer you to the section advisors for the young stellar objects group, because many young stellar objects have emission lines that would be interesting to follow. One field that I was involved in for about 20 years was BE stars, or gamma cast stars. And those are stars which have emission lines in the spectrum. And basically what we were doing was obtaining simultaneous photometry and spectroscopy over many years. Now, the problem that developed was that the few professional observatories that were doing this kind of long-term monitoring, it was not considered very sexy, and so it tended to be shut down and no longer done. And so there would actually be a place within organizations like the AAVSO with skilled amateur astronomers who learn spectroscopy, and I'm not a spectroscopist, to pick up this kind of thing here. I mean, we know that Mira stars have very interesting spectra. Again, though, that's a very slow process because a typical Mira star has a period of 300 days. But there is interesting stuff to do, and I would refer you to the spectroscopy section or to advisors of, say, the cataclysmic variables section or young stellar objects to see what they would suggest.
Great, yeah, good advice. I would like to go ahead and insert a little bit of a promotion here because we do have actually a meeting coming up on the topic of doing spectroscopy in the context of the AAVSO for our spectroscopy database, which is relatively new. And these kind of projects are definitely encouraged, doing spectro and photometric monitoring of the same stars. Like Professor Percy was just saying, that is something that often gets defunded by professional observatories, but amateurs can pick up the slack. So if you are interested in being one of those observers or just improving your spectra, we have a meeting on Tuesday at noon Eastern time, which I think is 16 o'clock UTC. And the link to join that meeting was recently sent out in an email to all AAVSO members. So
I'm just looking at my notes here, and there was one thing that I was going to mention and didn't. I did mention how you could track the changing period of stars through using the wavelet part of VSTAR. But when the data has gaps in it, then that method doesn't work very well. And there's a tried and true method called the O-C diagram, which many of you have perhaps heard of, where even if you have gaps in the data, you have a reasonable chance of being able to follow period changes. I refer you to my textbook or any other source like the AAVSO website about how that works. And I know that at least one person who's been working with Horace Smith on variable stars has been using the standard O-C method, which works very well, as long as you have groups of data that can be used to figure out what's the time of maximum, what's the time of minimum.
Yes, absolutely. As a matter of fact, on the topic of O-C diagrams, we had an excellent webinar presented by Gary Billings. It was one of these how-to sessions, and the recording is on our YouTube channel. So if you're curious to learn more about that, go check it out.
That's something that could potentially be done with the DASH data, at least on Mira stars, where they have a reasonably high amplitude. I'm not quite sure about the scientific value of doing it randomly, but maybe looking at some of the stars in the Percy list or others that are recommended on the LPV section website might be useful.
Great, thanks. Okay, so next question here. Let's take one of our questions from Facebook. So first one came from Sovan Acharya, who asked, I have no telescope. Without a telescope, how can I participate in AAVSO research projects?
Exactly the way I've suggested, by doing analysis of data that's accessible from databases. You don't have to make the measurements yourself. You just go to databases like the AAVSO or ASAS-SN or DASH or other ones like that. You take the data, learn how to do the analyses like I sort of outlined during this webinar here. So yeah, it's good for people who don't have a telescope. It's good for cloudy nights. It's good for climatically underprivileged locations, et cetera, et cetera.
Yeah, absolutely. Okay, and next question here coming from Marco Silva. Is U Monocerotis a confirmed eclipsing binary? I've been observing it for almost a year and I've read a lot about it. And I read your book, which is one of my favorites. So thought you'd want to hear that part.
The name is familiar, but I honestly can't remember what kind of star it is.
Okay. All right.
Quickly look it up in my textbook.
Okay.
Questions coming.
Okay. Next question here comes from Yogesh Chavan, who asks, how do you tell if a variable star is periodic or not periodic by its light curve? And Yogesh, if I misinterpreted your question, feel free to put a clarification.
So read the question again.
How do you tell if a variable star is periodic or not periodic by looking at its light curve?
Well, assuming you know its period, you calculate a phase diagram and see whether the phase diagram has any scatter. That's how I would define a star as being regular, if it has a really good phase diagram, and irregular if its phase diagram is more scattered than the errors would suggest.
Yeah, it's a good technique. Okay, and next question here. Has anyone performed a study?
Oh, hang on.
Go ahead.
Oh, so it was just UMON that the question was about. Is that right?
Yep, that's correct.
Oh, okay. Okay. I thought it was some other star. Well, there's actually a recent paper, and it's referenced in my JAAVSO article, that establishes that it's a binary system, and the dust is actually around the whole system. It's not just around the companion star. Sorry, I missed that question.
Interesting. Thank you. Okay. Oh, yes. So has anyone performed a study comparing the results coming from visual observing with those coming from CCD or CMOS photometry?
Well, I think the answer is yes. There's been quite a few studies that use both. It's a rather complicated question because the visual observations will have errors, and some of them depend upon the characteristics of the observer's eye and so forth. And I mean, what you normally would try and do is that you try and average the visual observations in bins. And in principle, that would give you mean values that were almost as precise as photoelectric values. It actually reminds me, and this is another tiny little story here, of one of the first students I had who was actually doing that kind of thing on a very famous variable star called Rho Cas, which is a hypergiant star. It has it's like a Cepheid, only its period is something like 300 days. And he and another student were comparing the visual observations binned with photoelectric. And the interesting thing is that he's gone on to a brilliant career in climate change. He's a Harvard astronomer, also known as Dr. Cool, because one of his ideas is to cool the Earth by seeding the upper atmosphere with highly reflective material. He's very often on legitimate TV talking about unusual approaches to climate change. So he survived working with me and went on to a brilliant career doing other things, as many other of my students have done.
That's great. Okay, so next question here. This one comes from Leo Fernig, who had asked a question earlier. He asks, you mentioned that the period and amplitude taken together is not enough. Could VSX be recording additional data such as the secondary periods? And is there a systematic way of recording this data somewhere out there?
Well, it would certainly be valuable if VSX was to record other information that was available. There are some stars that are very regular. I mean, most Cepheids are very regular, but some of them aren't. Some Cepheids are what we call double mode Cepheids. They have two periods going on at the same time. And that's always a good thing because two periods give you twice as much information as one period does. In particular, you can use the ratio of the two periods and plot that against the longest of the periods. And you get something called a Peterson diagram. And this is something where you can compare the observed results with theoretical models and find out things like the composition of the star, or the mass of the star, and so forth. So yeah, it would be great if VSX contained any important information and reference to any particular star.
Yeah, that would be a great improvement. Okay.
On the other hand, that's a lot of work, and VSX is primarily a volunteer effort. So I don't want to dump too much on the.
Yeah, true. And it's an impressive effort too.
It is.
The more I get into astronomy data science, the more I'm in awe at what they've managed to do. Okay, next question here. This one is a little bit broad, but maybe you want to give just an overview, particularly focusing on LPVs. Why are there fluctuations? What is causing the fluctuations in the brightness of variable stars?
Well, it depends on which kind that you are talking about. There's fairly simple cases like the rotating variables that have big spots on them, or either dark spots or bright star spots. So as the star turns around, then it varies with whatever the rotation period is. There's a nice little thing on the AAVSO website that I and John Rice did about rotating variables. The pulsating stars, those are a thermodynamic thing. The outer layers of the star, where material is going from ionized to neutral, this can power a thermodynamic effect, sort of like the motor that causes stations to grow to some particular level. Then there's supernovae, which are gravitational collapse of a massive star, or eclipsing stars, of course, where you have two stars going around each other. And if they are just stars, then you get a nice regular eclipse curve. But if they're one of the stars is dust enshrouded, then you get what I showed you for UMON and so forth. So it depends. Do get my textbook or some other. Some of this is on the AAVSO website, or generally Wikipedia is reasonable for topics like this. I wouldn't recommend it for extraterrestrial life or anything like that, but
Yeah.
for astrophysics, it's usually good.
Okay, great. Thank you. Okay, now we had another comment from Michael Poxon. Sorry, Michael, I don't remember what the context of the conversation was when this comment came in, but he said that there are lots of binocular variables out there, including Y Linksys. So I wanted to mention that one in case you have any comments on Y Linksys. Okay.
Well, there's even variable stars that you can observe with your unaided eye.
True.
Those are very often something that's useful for getting people started with an interest in variable stars. I mean, if you can take them out and show them that Betelgeuse is hardly visible anymore because it's down to plus 1.5, or you can schedule a minimum of algol or something like that. And a couple of years ago, one of my students, Sarah Bimo, published an interesting article in JAAVSO on what you can do with your smartphone. Just a standard smartphone in downtown Toronto. You take an image of Cepheus and you can measure delta Cephei on consecutive nights, or on how many ever nights you can get observations, and you can do your observations that way. You take your image and then you can go inside and actually do your comparison with the comparison stars. It does have some advantages.
Oh, that's cool. That sounds like a great way to get high school students started at schools that can't afford a telescope.
Mm-hmm. Well, that's another problem. A lot of schools have somehow bought telescopes and they don't know how to use them.
Yeah.
It happened in Ontario, Canada, some years ago when the curriculum changed, and with very little notice, the schools were all told to go out and buy a telescope. And they bought telescopes. The telescopes are all in closets somewhere because nobody taught the teachers how to use them. And the problem, of course, is the stars come out at night, the students don't. So
Yeah, that's too bad. A lot of wasted potential there. Okay, now we had one more question come in that I do want to address, but I think we might need a bit of clarification from the asker. So Yogesh Chavan was the asker and asked, what is the theoretical maximum variability that a pulsating red giant can have such that it's habitable for a long period of time? So I think perhaps Yogesh was asking about how long can a habitable zone persist around a red giant that's pulsating, you know, before the pulsations are moving the habitable zone too much that a planet can't stay in it. That would be my interpretation of the question, but Yogesh, if you want to submit a clarification, please feel free to do so.
well, yeah, there's a whole bunch of aspects to that question. One is that although stars like Myra have a very large visual range, their range in luminosity is much smaller. It's just that the visual portion of the spectrum has absorption bands in it that coincide with the peak sensitivity of our eye. So it might have a 10 magnitude range in visual and maybe only varies by 50% in its actual luminosity or its far infrared. So that's one thing. Then another thing, of course, is that it's constantly getting bigger. And so there might be a planet like Earth that's far enough away when the red giant is just starting its expansion, but at some point it's going to get eaten up by the outer layers of the star. Stars like Myra develop very strong stellar winds. I'm not sure what effect that would have. But there's actually a very interesting question that I and my students are trying to address right now. And it actually has to do with the long secondary periods in red giants. And what we find is that there's a fairly tight relationship between the long secondary period, which according to Szynski would be the orbital period of the companion, and the luminosity, which depends upon the radius of the red giant. And the fact that there's a tight relationship means that this companion must exist at some more or less constant distance from the star, like maybe 1.5 stellar radii. They can't be scattered out at different distances like Mars, Jupiter, and Saturn are in our solar system. So it's actually a problem that I'm trying to figure out, because my winter work study student, Julia Kim, has found a very nice relationship between the long secondary period and the luminosity in Omega Centauri, which is the biggest globular cluster. And it's not obvious why there should be this tight correlation. There's always a tight correlation between the pulsation period and the luminosity, because both of them depend on the radius of the star.
Interesting. Interesting. Well, thank you. Okay, and looks like this is our last question here, and I think this one is probably more addressed at me. So Peter, a newbie, had asked, can we have at some point a practical session on accessing the data and analyzing it with VSTAR or similar software? So more like a tutorial session, I suppose. And my answer to Peter is that as far as I know, we don't have one planned right now, but we are quite interested in planning one. So keep an eye on AAVSO communications, and hopefully we'll have that sort of tutorial session scheduled for you soon. And also, Peter said, thanks, John, for an awesome presentation. And I have to second that. I've seen a lot of thanks coming in through the Q&A and also on Facebook. And I can understand why, because this was fascinating. Okay, one more thing here. Timothy Weaver commented to let Peter know that the AAVSO does have a course on the topic of using VSTAR. And that's a great point, Timothy. We do have a choice course, I believe, on the topic of using VSTAR. So if you look that up on our website, that could give you a great starting place. Okay, and with that, I think that concludes our Q&A. So I'm going to go ahead and put up our closing slide here and start with the most important of all closing announcements, which is an enormous heartfelt thank you for Dr. John Percy for being the instructor of such a wonderful session today. We really appreciate it.
Well, thank you.
Okay, let's see. I would also like to thank again our sponsors before we close things down here. So that's Voice Astro and Chroma Technology. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. You can check out their website to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation and surgical devices, machine vision, multispectral imaging, and our favorite, astronomy. Okay, good news for everyone here. Today's how-to hour has been recorded. If you hop on over to our Facebook page, you will find that the recording is already there, available for review. And before too long, you will also be able to find it on our YouTube channel, where it will join a wonderful archive of dozens of other educational webinars just like this one. We have tutorials on every mode of observation, from visual to DSLR to advanced CCD photometry, so it's a great place to learn how to get involved. You can find us on YouTube under the username AAVSO HQ. And with that, I would like to close with one last huge thank you to Dr. Percy from all of us here at the AAVSO. We appreciate you and everything you do. Thank you.
And I appreciate the AAVSO too.
All right, see you all next time.